mean by opposite? Okay, we'll go through and look at your charges. If we're adding H and OH, hopefully what you see is we're having H plus and OH minus. Okay? We'll now go back to your other structure, your nucleophile in this case, and do the same thing. Apply charges to it. Yes, there's no charges there, but look at where the electrons are. We're looking at a reactive pi bond, and it can either go towards that carbon or it could go towards that carbon. When you draw out your resonance structures, hopefully what you would see is that your electrons will favor fairly heavily putting the negative charge out on the end and the positive charge on the inside. Okay? You should hopefully recognize that. Okay? Once you've done so, well, now what do? Positives and negatives, you just hook them up. Okay? In this case, the boron reagent does the opposite of what you would expect. Well, what would I expect? I would expect the hydrogen and the negative to hook up and the positive and the oxygen to hook up. Boron does the opposite, meaning I'm going to put the oxygen over here. I'm going to put the hydrogen over here. All I've done is react one pi bond, so the other pi bond is still present. Okay? This is now an enol, and what we need to remember is as soon as we form that enol, it tautomerizes, which is a fancy way of saying you convert the alcohol to the carbonyl.
Why does it do that? Because of the peroxide? That's step 2?
Nope, it has nothing to do with that. The why it tautomerizes is because the ketone is more stable than the enol. Okay. Everything about the ketone actually supports that charge balance, and it maintains that form. Officially, you could actually go through and run this reaction and do 2 additions of H and OH across the pi bond, and you would end up with this structure. The reason we don't talk about this structure is that this is known as a hydrate. It is an unstable form for a carbonyl, and what it very quickly does is it reverts back to the carbonyl compound. The hydrate form, or this particular structure, we will discuss in second semester.
So you would get the geminal diol before you get the enol?
All depends on how you want to look at it mechanistically, and ultimately we probably aren't going to be able to see that mechanistic detail. All we know is that we don't end with the geminal diol. We don't end with the enol. We end with the ketone, or in this case, the aldehyde. We end with that carbonyl compound. Okay. How we get there, we haven't worked out as much detail. There are 2 possible routes that would work. We could run tests to figure that out, but why? Is ultimately the answer that comes out of it. Okay. Does figuring that out add our knowledge to be able to do anything else? And at this stage, people have said no. So we don't worry about it. Okay? The same logic applies through to pretty much everything else. You're adding H and OH, and you add it in the opposite direction that you would expect. Okay? And that's largely because our hydrogen is getting added first as the negative, and that's why we're getting this weird kind of arrangement of species. If you evaluate your electrons, you can get to the answer faster than if you just memorize answers. Okay? That's my story, and I'm sticking to it. Okay? You don't have to believe me, though. It should look kind of similar to other reactions. What other reagents also add H and OH? Exactly right.
Mercury?
The mercury acetate
Acid and water?
with water, followed by the second step of the sodium borohydride. Would add H and OH. Those add it in a standard fashion, or in the normal fashion, though. Okay, so we'd be putting the positives with the negatives, and the negatives with the positives. So everything kind of makes sense in those additions. What else would add H and OH?
Acid and water.
Whoops. We could just go through and say straight up add water. Water isn't strong enough to react with a pi bond. What we would need to do is add a strong acid at the same time. So we get 3 reagents that add H and OH across a pi bond. They all add with slightly different results. When we use the strong acid in water, we form a carbocation. Why are carbocations dangerous? They're reactive. How? Yep, but everything wants electrons. Almost everything. Ryan should know this answer because we just talked about this.
They're very unstable.
Why? What do I started to say it. What do carbocations do?
You want to say rearrangement is what you want to say.
Carbocations can rearrange. Right? They could also do resonance. Okay, so the issue with carbocations is that positive charge can move throughout the structure depending on the structure. Okay, so that's not a particularly nice thing. So water and sulfuric acid are not a good synthesis reagent because of that possibility. So we could look at the mercury reagent. We end up shifting to something much more toxic, but because I never form a carbocation, I don't get any rearrangements. So the mercury reagent adds H and OH in the exact same locations that sulfuric acid and water would, okay, but without a carbocation. So no rearrangements. That's nice. Okay. The boron reagent also has no carbocations, but it places the H and the OH in the opposite locations. So those three reagents very commonly show up on the ACS as multiple choice answers. So they might give you a reaction and say, which of these reagents does this? You have to be able to remember what each of those reagents do and what are the complications that could come out of them. So they could show a reaction where a rearrangement occurred. That has to be water and sulfuric acid. Right? They could show it where no rearrangement occurred, right? Where it was possible for a rearrangement to happen. That then means the mercury reagent was used. Okay? So recognizing those patterns and trying to look for them and seek them out can help you get through this. Okay? The last thing that we'll do with our boron reagent, we can look at the full, gory, detailed mechanism behind it. What I've shown you has been kind of hand-wavy and not technically correct, but it gets you to the answer relatively quickly. Whereas if we look at the full-on mechanism, it's a little bit more detailed than I talked about. Okay? So if you want the full mechanism, both our textbook and the slides have that full mechanism. I don't see the value added in really going into detail behind it. The biggest important part is that stereochemistry is retained. All of these things happen on the same side of that reaction, so we maintain stereochemistry through the course of that reaction. Okay. The next part is looking at our reduction and oxidation reactions. Okay. As we learned from Gen Chem, we've got gain of electrons and loss of electrons, okay, or loss of electrons. Of course, I have those organized backwards. So we switch that. Gain of electrons is reduction. Loss of electrons is oxidation. Okay. So let's take a look at the reaction. Which one is it? What was reduced? What was oxidized? How do you do it in Gen Chem? Like, I don't know. I skipped that part in Gen Chem. Blocked it out of my memory. Okay. Typically what we would have to go through and do is look at the formula. So if we looked at our first compound, it was C5H6, okay, with a 0 formal charge. We could go through and determine what the charge was on the carbon or the oxidation state of the carbon in that formula and then the oxidation state of the hydrogen. And we could then go through and do that with the same thing on the products. The issue with that is that makes the assumption that all of those carbons have the same oxidation state, which is actually wrong. Right? So we can't use the standard format that we've done in Gen Chem. We need to come up with some other way to do this. This is what I already alluded to with our reduction and oxidation. Look at your structure. Oxidation is usually the easiest one. Oxidation is an increase in oxygen bonds. That's why we called it oxidation. Why do we call it reduction? Because we decreased oxygen bonds. Okay? So those definitions could help. Looking at our reaction, how many oxygens were changed? 0. So it doesn't quite help. So we could go through and look at the opposite. When we're doing our reduction and oxidation reactions, yes, we are changing our oxygen theoretically, but we're also changing the hydrogen in place of the oxygen. So we can look at a reduction as the increase in hydrogen bonds, or an oxidation, the decrease in oxygen bonds. So when I transition from left to right, what is happening? Okay, this was C5H, what did I say it was, 6? Pretty sure I did that wrong. This is C5H10. What did we do? We gained hydrogen. So what happened to our organic structure? It was reduced. And we refer to this reaction as a reduction reaction, no longer redox. In Gen Chem, we always said redox, they have to happen at the same time. That doesn't change. Things are still happening at the same time. However, in OChem, what do I care about? Only the organic molecule. So I keep my focus on the organic molecule and how it changed. So if I know these kind of increase in hydrogen, decrease in hydrogen to help, that can help me define which is happening in each of those reactions. The last thing that we'll add here is that it's not so much just oxygen, it's really in any electronegative bonds. Right? And in particular, more electronegative than carbon. Why carbon? Because it's organic chemistry. That's where our chemistry is happening. Okay? The last way we could go through and do this is looking at oxidation states. It's not fun, but if you were asked to determine oxidation states, you could do it. It's reference to homolytic minus heterolytic gets you oxidation state. If you want help with that, go to your textbook. If you want help with that beyond the textbook, talk to me in person and I'll help you with oxidation states. It's not worth any more trouble than that. The next part, label these as reduction, oxidation, or neither. 6 questions. I think 30 seconds is reasonable. How should we go through and do this? Okay. We do it the same way we should be doing all of our reactions. When we're predicting reagents, we need to identify what has changed. If you know what has changed, that can give you a hint towards what reagents you need to use. It can also help you decide what mechanism happened. If you know the mechanism, you can then predict and answer other questions. Okay, so let's take a look at the first reaction. What's happening at the first one? Let's call this number 1. Okay, what changed? Okay, I've got an extra chlorine. What was that? We also lost a hydrogen. Okay, we had to replace that hydrogen with chlorine. So we decreased the amount of hydrogens. We increased the amount of chlorines. What's the relationship between chlorine and carbon? Chlorine's a more electronegative. So what kind of reaction is this? This is an oxidation reaction. Okay, kind of makes sense? Next one. If we go straight down, number 2. What changed? Okay. Okay. Lost a chlorine, gained an oxygen. Not OH, we gained an oxygen. Why do I ignore the H? The H isn't bonded to the carbon. Where the chemistry occurred was at the carbon. Okay? It is that bond that changed. That's where my focus needs to be. I don't care what's connected after that. It could be a million different things connected to it. It doesn't change that that's where the chemistry happened. So what happened? Nothing. But didn't something change? Yeah. That something just doesn't happen to be reduction or oxidation. Did not change the number of hydrogens, right? And I did not change the fact that carbon was bonded to a more electronegative element. So the bonding to electronegative elements didn't change. Right? What type of reaction did I do? This is a substitution. Right? So if I can recognize the patterns behind these, I can help predict these things and potentially pick up reagents. The next one down, 3. What changed? I have an oxygen and gained a hydrogen. That would mean reduction. Far right top. How many hydrogens did I lose? I had to lose 2 hydrogens, okay, which would mean oxidation. But did I increase bonds to electronegative elements? Yeah, I did. Those are now sp2 carbons instead of sp3. And what's the difference between sp3 and sp2? sp2 is more electronegative. So yes, I did actually change the bonding to an electronegative element. Okay? So it's tricky, it's sneaky, but it's there. The next one. What happened? Gained a bond to oxygen at the expense of a hydrogen. So we're looking at oxidation. Last one. I gained 2 bonds to oxygen, so technically this was 2 oxidations. Okay? So looking for the patterns behind these reactions can help you predict what happened. Minimally, on a multiple choice test, you could go through and be like, well, I know this is an oxidation, and I know this reagent does substitution. Well, that means the substitution reagent is wrong. Okay? So you can use that information to your advantage. Take advantage of it. Don't just ignore it. Okay? Which sets us up with our alkene oxidation reactions. There are a multitude of them, or really 3 or 4 of them. Okay? For our oxidations, we're starting and branching out from this structure. So our MCPBA, our osmium tetroxide, permanganate, and then we have ozone. Any of those stand out to you as potentially problematic? One stands out to me. Permanganate shows up twice. Well, that's not a big deal because they have the same products. Oh, no, they don't. Okay, well, what's different? Temperature is really it. Okay? If you're hot and concentrated, you do lots and lots of oxidation. If you're cold and dilute, you do a relatively tiny amount. Okay? So recognizing the rest of those conditions can really dictate what changes after the fact. Okay? The osmium tetroxide is almost always followed up by a second reagent. Unfortunately, people are very inconsistent with that. If you see OSO4, do this reaction. Just make it a diol. Just do it. Okay? Sometimes you'll see a secondary reagent, sometimes not. Why is the ozone a tricky one? Well, what happens when we react to ozone, O3? Number one, we form a crazy weird looking structure with lots of oxygen in it. Okay? That structure is insanely unstable. Okay? And if we leave it to its own devices, we would run an oxidative pathway, meaning we fully oxidize. We end up breaking the alkene entirely and replacing every bond we possibly can with oxygen, and then saying, well, do I have hydrogen connected to those carbons? I'm going to make them oxygens too. Okay? So really, really insanely oxidative. That reagent is very similar to what we saw happen with permanganate. Does the exact same thing. Okay? If we instead move under what is known as reductive conditions, okay, we still do an oxidation reaction, but the oxidation reaction isn't quite so severe. See how there's that hydrogen there? In the bottom case, it was turned into an oxygen. In the top case, left is hydrogen. Okay? To be reductive, we have to have something except the oxygen. Okay? Something has to run away with that extra oxygen. That something is typically DMS. Why would we abbreviate DMS? It's not that big of a deal. If it picks up an oxygen, it becomes DMSO. Where have we seen DMSO? That's a solvent. Okay? So that is typically how the reductive condition gets asked. Is they go, oh, what else is formed? And it's DMSO. Okay? So lots of things are happening within this. Ultimately, all of these are going through a cyclic intermediate structure. Okay? If we look at our patterns between these, we're starting with pretty much 3 atoms with lots of oxygen. Why would we need lots of oxygen? Why do I need lots of oxygens? What happened in this step? Oxidation. And what do I need to do oxidation? Oxygens. Okay, so all of these have in common oxygens. We need those lots of oxygens to do the oxidation reaction. Okay? The metal usually is sitting in the center with oxygens on the outside when the metal shows up, like potassium permanganate or osmium tetroxide. They're following the same patterns. Okay? What is the leaving group in each of these cases? It's a lone pair of electrons. It's ultimately the pi bond shuttling out. Okay? That is such a tiny group that we get an immediate attack back by the rest of the structure. So we do not form a carbocation, and we form these nasty big intermediate structures. Okay? So if we looked at our pi bond, the electrons can come out, shuttle across, and shuttle back down. The electrons come out, shuttle across, and shuttle back down. Okay, so it's a question of looking at those pieces and trying to recognize those patterns. Okay. Quick reference to Diels-Alder. Diels-Alder is doing pretty much the same thing. We take a pi bond and we react that with an electron source. So our electrons can come out, shuttle around, and come back down. The same thing is happening with our metal oxides. The Diels-Alder is officially second semester material. It's, for whatever reason, on Maricopa's competencies to be discussed, which is why you have that video to watch it and see those patterns behind it. Okay? It is also spatially probably the most difficult organic chemistry reaction, in my opinion, okay, because of all the spatial stuff that goes into it. It's chapter 5 on steroids. Okay. Our dihydroxylation mechanisms. Okay, so one thing that comes out of this is you can see these big words. Dihydroxylation. Ation meaning doing something. Di meaning 2. Hydroxy, OH. So what are you going to do? Put 2 OHs on your product. Exciting. Wow. Look, the name can give you that if you pay attention to the name. You don't want to pay attention to the name, that's okay. You just got to watch out for the next part. Okay. If we look at our osmium structure, or for that matter our permanganate structure, because it's going to follow the same pattern. Okay. The electrons from our pi system come out, react with the oxygen, and shuttle electrons around to the other oxygen. That oxygen can quickly donate back down, and we never form a carbocation. If we look at the product, we have a stereocenter. In fact, we have 2. So we would have to specify wedges and dashes. Notice to the osmium structure, they're both wedges. Why is one not dashed?
Because it's not anti-attack, it's cis-attack.
Okay, because it's attacking on the same side, so they should be on the same side. I'm holding up my right hand because I'm not holding up my left. That's true. That doesn't explain why I'm holding up my right hand. Okay, why am I holding up my right hand? To prove a point beyond just looking at what happened and explain why it has to be like that. Okay. We're getting at the same concept, but entirely different reasons. Why do they both have to be on the same side?
Because it happens at the same time.
Okay, same time, concerted step. That's a good thing to add to it. Did I just hear because I made up the rules? I mean, that's kind of cool. I've made up the rules because I'm that special, but no, I didn't make them up.
Is it because the P orbitals are facing the same direction?
With our MCPBA, right, we formed an epoxide. If one was wedged, what's the other one? Why is it also wedged? It is the only way to possibly connect the structure. Okay? Why? I can't have one wedge going up and one dash going down and somehow connecting at the same thing. It doesn't work. Okay? With a 5-membered ring, We now increase the chances of that potentially happening, but even then, physically, that's going to be really difficult to pull off. Okay? So it makes sense for them to both be wedged. Okay? Add to this the patterning behind it. We said the leaving group is insanely small. It's a pair of electrons. Because it is insanely small, I need something to immediately stabilize. What would immediately stabilize? The carbocation that's immediately there, so I never form it because it immediately hooks up. It's part of why it's a Syn addition. Okay? Kinda, sorta. Kind of like our boron reagent. It's doing the same thing. It has to attack on the same side because our leaving group is too small to break off, spin around the entire structure to get to the other side to do another backside attack. Right, so we're locked into that conformation. You'll notice after that, they stop showing a mechanism. Why? Because osmium's a metal, and it's not so much we don't care about metals. The reason we haven't studied them as well is because they're confusing. So we skip it and just say some stuff happens and we end up here. Okay? It's a bit unfortunate, but that's how we do a lot of things. We can come up with some arrows when we bring in metals, but ultimately we aren't very good at understanding how those electrons are specifically moving into what orbitals or to what bonds because metals have access to the d orbitals, okay? And sometimes to the f. Okay? So if we take a look at the bottom reaction, that would be a bit of a silly question to ask because it should be a little bit faster than that. Yeah, that's literally the reaction shown above. It's the same one. So let's not do that. Okay, so let's move on to the next reagent, permanganate. Okay? We have an alkene, and then I have permanganate. Well, if I look at permanganate, I have the metal with 4 oxygens around it. That looks an awful lot like the osmium tetroxide that we just looked at. And so what happens? The exact same thing. Okay? No difference. It reacts with the pi bond. We form a goofy intermediate that quickly decomposes and leaves us with my precious, with the oxygens on the same side of our formal double bond. Okay?
In the previous slide, when we have underneath the arrow,
Mm-hmm.
H2O2, so that H, that hydrogen in the product, it comes from H2O2?
So the hydrogen to finally protonate probably comes from one of those species. I would guess it better to reference probably the alcohol than the H2O2.
Do we need to know?
No. Nope. This is where we're forming that cyclic intermediate. The result is that we end up with the diol. We have 2 oxygens attached. We just get rid of the metal. Just delete it, put hydrogens there. Okay. Which I know seems really excessively silly, but we now have 45 plus 75 minutes. 45 for the rest of today, and then 75 on Wednesday. So that's kind of where we're stuck at. Okay. Permanganate does the same thing. Exact same chemistry. We form that cyclic intermediate. That cyclic intermediate decomposes and gets us the diol. Okay? And again, it's on the same side because what we're leaving from the oxygen in that attack is a pair of electrons. Those are not stable. They have to immediately reattach back to the structure. Okay, so we get that concerted step. We end up with that product. Okay, the big thing that steps out here is it has to be cold and dilute. The base is a little bit less important, but it has to be cold and dilute.
Is that the major product?
That is your major product.
31% is that you form 70% of the banana?
Yeah. It's not necessarily a good reaction, but yes, that is your major product. One of the reasons why we run into issues is that what can permanganate do if it heats up? Something else. Okay, it does more oxidation, and that causes lots of side reactions. So we can get a bit of a mess. Okay? So if we were to look at, say, this reaction on predicting a product, Okay, what would happen? In our first step, we get rid of the pi bond. Come on, eraser. And we would replace it with, whoops, our permanganate, okay, being on the same side of the structure. Notice I'm not even concerned about the double bonds in there. It's not super relevant within the oxygen structure. Now what happens? Well, we can cleave the permanganate off and show a bunch of letters and then some more scribbles. And we'd end up with the Syn diol. Okay, we could go through and show wedges and dashes. The wedges and dashes become less relevant here. Why? There's no stereocenter. This is a double bond. It's an alkene. Okay, so we don't need to specify that. Extra little issue that pops up with this one. May help if we actually make this a little bit more apparent. Does anybody see anything problematic with this product? What do you mean continue? React again with what? Okay, let's go with your...
Starts with an R.
Technically, no.
Starts with an S. Pi about.
S and R were both wrong. Starts with a T. It's a tautomerization because what do we have here? We have an enol which quickly tautomerizes. Under the conditions, under base conditions, what will end up happening, that eraser's starting to get to me, is that, believe it or not, we will lose that double bond and it will be replaced with 2 carbonyls. Okay? So you have to watch out for that tautomerization. It will show up even with these reagents. Okay? The next one's kind of a fun one, our oxidative cleavage. Okay? So this means you take your alkene and you literally just break it in half. Okay? So just cut it and replace those bonds with oxygens. Okay, so let's take a look at that first one at the top. So the best way to describe that answer would be to redraw your structure, a little bit more space. And now I'm going to stretch that double bond out, make it really, 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 really long. I'm going to stretch it out because now what I'm going to do is bust in, stupid eraser, bust out an eraser, and now replace those with oxygens. Now what do I draw? The product. Okay? So you can do this for all of your oxidative cleavage. Okay? What happens when we move to the next one? With a triple bond. Well, triple bonds are non-polar pi bonds just like alkenes. They will also undergo oxidative cleavage. So what happens? Stretch out my triple bond a little bit. I would erase in between and drop in oxygens. What's the problem with that? Those oxygens would be charged because oxygen is happy with how many bonds? 2. So what does that mean? Okay. But if I get rid of the bond, now I've got a problem. I can't just lose the bond. I have to replace it with an oxygen because this is oxidative cleavage. I'm cutting all of those pi bonds. I have to increase or replace those bonds with oxygens. The end result ends up being oxygen bonds on your structure, or extra oxygens. Okay? They didn't show that very well in that product because they're referencing the carbonyl first and foremost, but the oxidative cleavage for an alkyne is going to drop in extra oxygens as well. Okay? It again depends on the condition, so we have to be careful there. Okay? So the reagents, KMNO4, permanganate, concentrated. Permanganate will continue through your reaction, do an extra cleavage of that bond, and end up with a fully oxidized structure. Okay? The last really important one would be ozone, does the same thing. Notice in the middle there, I've got the osmium tetroxide in really small font. Okay? Osmium tetroxide does not do oxidative cleavage. It'll break the pi bond to make the diol. The diol structure can now react with another reagent, periodate, to cleave the last bond, right, and end up doing the full oxidative cleavage. Okay, so if you sequence those two, you get the full cleavage. That's mentioned in the textbook in a little bit more detail. I'm just kind of going to leave it alone because it's a less used reagent. So our permanganate reaction, okay, again on our speed, we're now concentrated in hot. What are those things going to do? Okay, so we go through, we form our 5-membered ring, okay, and we would go all the way down, potentially, down to our alkene or our pi bonds. Okay. Why? Why does it continue? Okay, so what happens here? If we're concentrated, what can now happen? Okay, particularly if we look at our other reagents. We could have hydroxide or we could have water. Okay. What do both hydroxide and water have in common? Lone pair electrons on that oxygen, which could do what? They could attack the pi bond. The result being the diol. Okay. If we have a diol, now what can happen? Now that can react with our permanganate, just like it did before, and it can do another oxidation. The result is we go all the way down to the carboxylic acid. Okay? So if we have high concentrations of permanganate, it's present enough that it can react with the diol. If it's dilute, it can't react. Okay? That's why in our previous case we didn't do the full step through. Okay? What you're looking at here is what's known as your acetal formations, okay, or our hydrates, which we mentioned earlier in the class. Okay? That is all second semester material. It is all really, really fun because it involves equilibrium. Those of you that have seen that may realize it's not so fun. It is pretty much everything that happens in biochemistry. This is all carbohydrate chemistry. Okay? That's all second semester. Okay? And it's all driven based off of equilibrium. So pretty much everything you did in 152 shows up with a vengeance in second semester OChem. Okay? Oxidizing agent practice. 2 questions, a minute seems reasonable. Everybody was laughing at, what's wrong with my weird structures? Why are you guys laughing at those? Bow and arrow, okay. Remember how I gave you a hint? That hint was draw your bond really, really long and then just erase the middle. And then what? Add oxygens. All right. So by doing so, I've now got this structure set up with a quick hint on how to draw out the product without too much trouble. More than likely, you won't see it drawn like that on the ACS exam. Why not? Okay, one, it's a lot of paper. You drew this massive structure. Okay, so it would also be like really easy. You just be like, oh, that's all you had to do. That's the one, because that's where you just draw it long and you just erase. Right? You'd be, oh, that's obviously the answer. They aren't trying to be a jerk and remove the obvious answer. What is wrong with this structure? It's not so much angle strain now. It's not how it would look, because what have we shown? We've shown an eclipsed interaction within our Newman projection if we drew out our Newman. It doesn't make sense to show it this way. We would have to unfold it. 1, 2, 3, 4, 5. This is where counting your carbons can come in handy. 2, 3, 4, 5. And then I've got those carbonyls hanging off the ends. Okay? Is that the correct answer? Permanganate, I'm asking it, so clearly it's not, right? Is that what you're saying?
Because you're asking, I'm
Yeah.
saying and say no.
Yeah. Permanganate's a strong oxidizing agent. If it's concentrated, it's going to oxidize everything it can. Right? Which means if I have a carbon with hydrogens on it that is a potentially reactive carbon, what's going to happen? I'm going to get rid of those hydrogens. You mean like these hydrogens? Yes. Those hydrogens are on an oxidizable carbon. Why is that carbon more oxidizable than, say, any of the others? Why is it partially positive? Because it's bonded to the electronegative oxygen. That's what's establishing that chemistry at those positions. The blue ones don't react. The other positions will continue to react, and we'll replace those with O's. Okay. Where do I get the H from? Because wouldn't that just be replacing it with O negative? What's step 2? I add HCl, which is now why it becomes the carboxylic acid. Make sense? What happens with the second one? We do the same thing. We erase the middle out of it, drop in the oxygens, go through and count out our structure. We had 1, 2, 3, 4, 5, 6 carbons this time. 1, 2, 3, 4, 5, 6. Okay, I'm going to number left to right. Okay. Remember what we said for the ACS? It probably makes sense to actually number the other direction. Why? Because they're trying to trick you, and they're intentionally dropping in and trying to prevent the accidental correct answer. Right? At position 2, what do I know to be true? I have the carbonyl. What's at position 1? Well, it's connected to the carbon at 2. Okay. What's at position 6? My carbonyl. Do I have any oxidizable hydrogens? Yeah, where? Okay, I heard a suggestion at position 2, there's an oxidizable hydrogen, so let's go ahead and draw that hydrogen on so we can see it. It's not there because that would have exceeded the octet. There is no oxidizable hydrogen there. What has to happen? Nothing happens there, but the other location, there is. What happens? We'll drop in the OH. All right? So don't just assume it has to become a carboxylic acid, because that's not true. Okay? If there's hydrogens that are at that position, then you can convert them into OHs. If not, you can't do anything. All right, so what we're left with is a ketone and a carboxylic acid in our final answer. Make sense? Okay, let's try and break you. Like is a bit of a strong word on that. So if we went through and stretched out all of our double bonds, and then we tried to erase all of them out of the middle, and then draw in all these oxygens. Whew, that's a lot of oxygens. I even lost the structure in there. Deep size all around. Why'd you stop drawing, Jeremy?
That doesn't look right.
Why does it not look right? Elaborate. Aromatic rings. What do aromatic rings do? Massive resonance throughout that ring, meaning they don't react. Damn it, I drew all of that for nothing. Exactly. Now I know how you feel, right? Is that what you're saying? Except I already knew how you felt. I didn't have to prove it. We can stretch out that double bond, erase the middle out of it, draw on our oxygens. Okay. Do we still have oxidizable hydrogens? Yes. How many? There's 1. There's 2. There's 3. What happens? Erase them, turn them into our oxygens with our acids. What did we just make here? Give you some memory from Gen Chem, maybe that helps. H2CO3. That is carbonic acid. What does carbonic acid immediately do? It immediately turns into CO2. There's a little carbon sitting in the middle there. Okay, so we end up with 2 products. So we completely cleave that 1 carbon off. Because it still has tons of hydrogens, it gets oxidized the crap out of all the way out to CO2. You mean CO2 is the end of all oxidation reactions? Yes, but you knew that already because you breathe. And what are you exhaling? CO2. Why are we exhaling CO2? Because we are oxidizing glucose to generate energy so that we can live. It is that oxidation reaction that results in CO2 that actually allows us to survive. Right? That is our ultimate oxidizing compound. What happens with the second structure? Do we have an aromatic ring? Nope, which means? Yep, we got to go through and do everything. Okay. You'll notice that on this one I was actually kind of nice because, as everybody laughs at me, that wasn't nice. I drew the triple bond bent like that. That's a horrible way to show that structure because it's a linear carbon that is sp hybridized. You'll never see that on an exam, okay? At least an official standardized exam, because that is some bad structure drawing. Okay? It should be drawn straight out. Okay? So what do we go through and do? We erase our bonds. We drop in our oxygens. Now what do we have to evaluate for? Our hydrogens. Do we have any oxidizable hydrogens? Yes. In fact, we have an awful lot of oxidizable hydrogens. Okay, so we can then turn those into OHs because we're using a strong oxidizing agent. So I'll agree with all of those. I won't agree with the last oxidizable hydrogen because there's something else weird going on with that one. What is special about both of those oxygens? They don't like having triple bonds. So we actually already had the OHs added on those. Now I'll address that last oxidizable hydrogen. That can be turned into an OH. What have we now formed? Carbonic acid, which will immediately decompose into CO2. Nice fun way that this question gets asked. How many products are formed from the following reaction? Okay. Not which ones, how many. So your answer will be 1, 2, 3, 4. You only get 4 answers. Okay. And you would have to go through and look at how that structure could decompose, okay, and evaluate potential symmetry, because symmetry could make your product similar. So for the reaction we've got shown on the right, it comes out to be 3. Sorry, that sounded weird, but 3. Okay. Why 3? Because we split each of those. Every time we split, we generate 2 products. Those 2 products would still be connected to each other. Why? I only split 1 so far. Then I split the other side, and now I have 2. Oh, I've got the triple bond, so now I can split that and make 2 more products. So now I've got 5. No, it's still connected to the rest of the structure. Okay? So you have to realize how that breaks apart for those oxidative cleavage reactions. Okay? Kind of make sense? Okay. They could just as easily say which of the following are valid products. That is just as valid. I just wanted to give you a slight respin on that. Okay. The last one, ozone, does the same kind of thing as an oxidizing agent, right? But it does some really goofy chemistry. So the first thing that happens is the ozone directly adds like we would expect normally, and it forms that cyclic intermediate. Okay? That's the same as we've seen with all the others. Okay. That cyclic intermediate is known as the malozanide because diozonide was taken. Fine, whatever. We get the internal exchange of our double bonds or our ring structure to generate that goofy looking charge state at the far right. which continues to cyclize in on itself, and we end up at the very end of that reaction with our ozonide. Okay? You're not responsible for that mechanism. Okay? What you're responsible for doing is acknowledging that ozone is going to turn into carbonyls. It's going to do an oxidative reaction. Okay? That's the part that you need to know with your ozone. Okay? That's it. The mechanism is there in case you're interested in it. I think it is kind of neat. But again, now 75, 80, 90 minutes, we can't spend a whole lot of time on it. Okay? The big key step here is that notice, what do we still have connected that far right? We still have a hydrogen here. So why might we choose to use ozone to do this reaction instead of permanganate? The ozone will leave me at the aldehyde. Permanganate won't. Okay? Ozone gives me control over the possible products. Permanganate just says do it. Okay? So we have those two different stages depending on what we're trying to do. Why might we choose permanganate? Well, I don't care what it ends up with. I'm just happy with the result. I just want it to oxidize. Okay? Why would I choose to use permanganate at all? Because remember, ozone could go in two steps, where it ends with the H or it ends with the OH. Is ozone a particularly healthy molecule to be floating around? No, you've probably heard about it and smelled it, like you fried a computer or something, you're like, oof, you get that nasty whiff. Okay? That nasty whiff is highly toxic gas. Ozone's a gas reagent. Permanganate is in solution, okay, or a solid. Okay? So we can control the permanganate safety-wise much better than we can control ozone. So permanganate may get used more often than the ozone, but ozone's more selective. Okay? We get a little bit more control with it. The big tip-off with our ozone is that DMS, okay, often resulting in DMSO. And here it's DMS. Why is it DMS? Di, dimethyl. There's the two methyls, and then the sulfur gets named sulfide. That says sulfide. Just take my word for it. Okay? So it's looking at those pieces. The DMS is kind of your big step out. We could go through and not use DMS. Just do a full peroxide, and this is where it gets weird. Sometimes you'll see it written out as peroxides. I've seen it written as H2O, and I don't know if that's a typo or H2O is just fine. Okay? So if you see ozone without DMS, oxidize the crap out of it. Okay? Why would I choose to use ozone? Because it doesn't oxidize the crap, because I can stop here. Okay, so it's better to remember ozone is stopping and permanganate is going. Is probably your best shot. Kind of makes sense? Okay. Of course, since we've oxidized, now what do we have to do? Reduce. There are tons of reducing agents that you will see in second semester. In first semester, we really only keep it to 2, sort of 3. Okay? The first one is at the very top. Okay? Arguably, what I would say, oh, come on, pen. The first one is at the very top, which I'm circling 2 arrows. You see H2. What are you probably going to add? Hydrogen. How many hydrogens would you add? 2, because it says H2. Yep, that's about it. With platinum, palladium, or nickel. Sometimes you'll even hear it referenced as rainy nickel. All of those metal catalysts will do the same thing, okay, as far as you're concerned. They will add hydrogen across a nonpolar pi bond. Okay? The next 2, whoops, and actually Lindlar. Nope, never mind. The next 2 do something slightly different. H2 with Lindlar's catalyst. So sometimes you'll see it written out as Lindlar. Okay, you may also see it referenced with barium sulfate or something in addition to platinum or palladium, like anything. Okay, I've seen barium sulfate, I've seen carbonates, you're just adding something else. You may also hear it referenced as poisoned. Okay? So if platinum is a normal human, healthy, that can do tons of hydrogen, if I poison that human, would they be as active? No. Why might that become important? Do we have nonpolar pi bonds with more than one nonpolar pi bond? Do we have nonpolar pi bonds in a structure where there's more than just one nonpolar pi bond? 50-50. Do we have a structure where I have nonpolar pi bonds, where I have more than one nonpolar pi bond? Well, there's my nonpolar pi bond, and I'd have what functional group? An alkene. Do I have structures where there's more than one nonpolar pi bond? Oh, you mean like an alkyne? Yes. Okay. Why would that become important? Well, the alkyne now has two pi bonds that can react. If we just throw hydrogen and platinum or palladium at them, what's going to happen? It's going to react them both. I don't want the metal to be as active, so what should I do? Make it less active. Right? This guy keeps punching me. I'm going to make him less active by cutting off an arm. Now he punches me less. Right? Poison it. Lindlar's catalyst is poisoned platinum or palladium. Right? It prevents further reactions. Meaning, if I use H2 in Lindlar's, it will react and remove a single pi bond, and that single pi bond is only part of the alkyne functional group. It's then left with an alkene. Lindlar's catalyst is too weak to beat up that pi bond, and I'm left with the alkene. Okay. The last one on our list, so our barium, our poisoned one, is alkyne specific. The last one is also alkyne specific. Why do I need two reagents for an alkyne? One to break all of it. What did the H2 and platinum, palladium, and rhenium nickel all do? Broke all of it. Okay, that reacts with both the alkene and the alkyne. Those are entirely non-selective, and they will react to any pi bond. Okay, even our carbonyl compounds. Okay. Why might I need a special reagent for the alkyne? What happens when I remove or add hydrogen to that pi bond? What have I now generated the potential for? Cis and trans. Depending on how the hydrogen is added, I can end up with the trans alkene, or I could end up with the cis alkene. Lindlar's catalyst is adding H2 the exact same way it's added in the top one. H2, good leaving group, bad leaving group. Bad, because it would be H minus. That ain't good, which means tacks on the same side. Right? Because Lindlar's is doing the exact same thing, it's adding the hydrogens on the exact same side, which means the product I would get would be cis. Okay? That's not the energetically most favorable product, and what if I wanted the trans? Okay, well, I'd be kind of dead in the water until someone came up with sodium metal and ammonia, and that will do alkynes to trans alkenes. The poisoned one gives you cis alkenes. Okay? Very subtle change in the end result, but that exceptionally often is tested. Okay? Because it's not easy to get that system. Why might it not be easy? You're literally adding H2, tiny molecules. You would think that has to go in a cis type formation. okay, or Syn type addition. How do all of these, except for the last one, work? Your catalyst acts as a substrate that connects both hydrogen and your pi bond. So they both connect to the surface, and it facilitates the transfer of electrons between the carbon and the hydrogen, placing the hydrogen on our carbon. Okay, we would then have a very weak connection here. Notice that it's no longer connected to the substrate, which means we could potentially rotate about that bond. Turns out that it happens so fast that the rotation doesn't happen. And we get the hydrogens added to the exact same side of the pi bond. Okay? That's the important part with our reducing agents, okay, is you're getting a Syn addition. You're adding the hydrogens to the same side. Okay? Alkynes do pretty much the same thing, but we get Lindlar's catalyst where it stalls after removing just one of the pi bonds. And then we'll also do the sodium metal and ammonia that get you the trans product. Okay? So there's our big summary that has everything on it. I believe not messed up. Yep, I think I've got that all right. Okay? So you should remember those, get them nailed down. Ultimately, what I would say is that it's really just memorizing hydrogen, platinum, palladium, or nickel as one reagent, which reduces everything, and then Lindlar's catalyst and sodium and ammonia. Okay, so it's really 3 reagents. Okay? Because most of these involve, again, metals, the mechanism becomes much less important because we don't understand our metals quite as cleanly. We know something about coordination, but we can't draw those very nicely. Okay? With one exception, sodium is not a pretty metal for this. So how would this reaction work? What am I adding across the pi bond? Hydrogens. Where are those hydrogens coming from? They have to come from the NH3, which means the NH3 is acting as an acid. And what did we say NH3 acts as? A base. Huh. So how can I make that basic structure act like an acid? What would it need to react with? Something that is more basic. What would be more basic than nitrogen? Okay. We've got an interesting idea coming out of this. Fluorine. Fluorine's more basic than nitrogen. Does anybody want to second that or negate it? That was the statement. Does anybody want to try and provide support for that statement or say no, that's wrong? Okay, why is that wrong?
HF is a stronger acid than NH3.
So the question is, why is fluorine a weaker base than nitrogen?
A strong acid.
It's not a strong acid.
HF?
No, it's a weak acid. You've remembered that HF is an unpleasant acid to be exposed to because it melts your bones.
Yes.
Okay? But it's not a strong acid.
Because fluorine's more stable with a negative charge.
What does a base need to do? Donate electrons. How do we evaluate the ability for any atom to donate electrons? We start with charge. Neither are charged, so we can then move to size. Is there a difference in size between nitrogen and fluorine? No. So we move to electronegativity. What is the difference in electronegativity? Fluorine being more electronegative. Cool. What does that mean about its base strength? It is now weaker. It's holding its electrons tighter, which means it can't act as well as a base. Right? So you have to go through those same sets of rules every single time. And Josh, is that you just in general, or are you being like, God, stop talking about that same thing?
Just thinking about it.
Okay. So, fluorine, bad choice. What's a stronger base than nitrogen? Why carbon? Okay, so if we first did a comparison and drew on 4 hydrogens, would you say carbon's a better base? No, why not? It doesn't have any electrons. So let's give it a lone pair. Let's ignore the charge for the moment. We'd move to size, no difference in size. So then we'd move to electronegativity. What's the difference between carbon and nitrogen? Nitrogen's more electronegative, meaning it holds the charge better, which makes carbon the stronger base. Why would I want to go after carbon and not, say, bring in fluorine, or for that matter, even oxygen? Take a look at my reagents. Does anybody see fluorine or oxygen? No. This is why carbon would be a natural good first call to go to, right? Because carbon is present in that solution. If we go through with its base abilities, it's also a better base. Okay? But carbon would need a lone pair of electrons. Okay? Therein lies an interesting dilemma. Because does it have a lone pair of electrons? No, it does not. We could go through and look at a resonance structure showing a lone pair, but the resonance structure explains something about the reactivity of it and the balance, but it doesn't actually exist. Okay? And so that lone pair, or the electrons in that bond, can't pick up the hydrogen, because then we form NH2 minus, and that's an even stronger base. Okay? So what else is present then? We could try and deal with moving down the column. Arguably, we know this reaction works. Work within the confines of the reaction shown. What else is present? Sodium. But sodium's always a spectator ion. Why would I care about sodium? When was the last time you ingested sodium? This morning? It was a nice vague question there, right? Last time you ingested sodium was probably never, because it probably would have killed you. Okay. But Tyler, you started to say yes. Why? What were you thinking of when you said
Sodium chloride.
Sodium chloride. What is the sodium in sodium chloride? Sodium ion. Sodium ion is a spectator ion. It's not reactive at all. Sodium metal, on the other hand, is insanely reactive and would probably explode you from the inside out. What are we reacting? Sodium solid, which means it's a metal. How is sodium metal different than sodium ion? It's not a spectator. Touché. It has one extra electron. What can that one extra electron do? It can react with the most reactive thing present, which will be the pi bond. What's the result? And technically I should draw that more appropriately. Oops, it's not a positive charge, it's a radical. What kind of bond would there be between carbon and sodium? An ionic bond, meaning sodium just completely gave up its electron to the carbon. Now sodium's a spectator, and what can I have? A negative charge. With a negative carbon, is that a strong base? Yes. Is that a stronger base than nitrogen? Yes. What happens? Now the hydrogen can get removed. And we'd form NH2 minus. Ooh, NH2 minus, that's not really good. Is it better than C minus? Yes. Reaction proceeds forwards. I now have a radical. Is that a stable structure? No. What would it need to stabilize? Another electron. Where might there be more electrons? Another sodium. But now we have an interesting issue popping up here. Okay, that lone pair now changes the hybridization of our carbon. Okay. In our radical structure here, what is the hybridization of the carbon? How many groups of electrons are around it? 2, because radicals act like carbocations. So that hybridization is still sp, which means linear shape. The instant I give it another pair of electrons, I will now have 3 groups of electrons, which means it's now sp2 hybridized. Because it is sp2 hybridized, it changes the shape, so now the R groups come into play. Where do I want the R groups to align? Why should they align trans? That is most stable. And because my intermediate effectively has a carbocation, the electrons will get dumped in such a way to generate the more stable structure. That is why I get trans. Okay? I can now bring in a second equivalent, of my NH2. The negative charge can come in, and I would end up with my final product with the trans product. We're moving through what is known as a radical anion. We have both a radical and an anion in the same structure. Okay? It's a fun little reaction if you like that kind of thing. Because we're going through each of those transition states, it becomes, or not transition states, intermediates. So we've got both radical curved arrows, which we haven't talked about yet, and double-headed normal arrows. So all sorts of fun stuff is happening in it. What do you need to remember? That. Sodium and ammonia react with the triple bond to form the trans alkene. Okay. The alkene is not reactive enough to react with sodium, so it stops at the alkene and we're done. Okay. There's the goofy full-on mechanism if you wanted. What we will see is the same reaction with aromatic rings, because while I said aromatic rings don't react, if you throw something reactive enough, like sodium metal at it, it does react. Okay? That is officially involving chemistry from second semester. It's the exact same mechanism as was just presented. Okay? We didn't do too bad as far as timing, because we're now at slide 57, so we went through 20 slides. We've got another 20 slides reserved